The dominant approach in sequence transduction models involves recurrent or convolutional neural networks, often enhanced with attention mechanisms. However, recurrent models face a significant limitation. Their inherent sequential computation restricts parallelization. To address this, we introduce the transformer architecture. The transformer dispenses with recurrence and convolutions, relying solely on attention mechanisms to model dependencies within the data. The paper addresses the goal of reducing sequential computation, a foundation also found in models like the extended neural GPU, ByteNet, and convolutional sequence-to-sequence, or ConVS2S. These models use convolutional neural networks as a basic building block, allowing them to compute hidden representations in parallel for all input and output positions. However, a key challenge is that the number of operations required to relate signals from two arbitrary input or output positions increases with the distance between those positions. Specifically, in convolutional sequence-to-sequence, the number of operations grows linearly with distance, while in ByteNet, it grows logarithmically. In contrast, the transformer architecture reduces this to a constant number of operations. By using a constant number of operations, the transformer simplifies computation across long distances. The transformer model employs an encoder-decoder structure for sequence transduction. As mentioned in the model architecture section, the encoder takes an input sequence of symbols and transforms it into a sequence of continuous representations. The decoder then generates the output sequence, symbol by symbol. This generation is auto-regressive, meaning that at each step, the decoder consumes the previously generated symbols as additional input when producing the next one. Let's dive into the heart of the transformer, its architecture. The transformer leverages stacked self-attention and fully connected layers to process information. It's built around two main components: encoder and decoder stacks. Which are the fundamental parts of this architecture? To enhance performance and stability, residual connections and layer normalization techniques are applied throughout the network. Notably, all sub-layers within the model, along with the embedding layers, are designed to produce outputs with a consistent dimension. Specifically, dimension equals 512. Delving into the specifics, the encoder is composed of 6 identical layers stacked on top of each other. Each of these layers contains 2 sub-layers. On the other hand, the decoder mirrors this structure with 6 identical layers as well. However, the decoder incorporates a third sub-layer specifically dedicated to attending to the output of the encoder stack. Crucially, residual connections and layer normalization are strategically applied around each sub-layer in both the encoder and decoder. This ensures that the network trains effectively and maintains robust performance. Let's delve into how the attention mechanism works, which is the core of the transformer model. As described in the attention section, the attention mechanism essentially maps a query and a set of key-value pairs to an output. The queries and keys are used to determine the weights. The values are then weighted and summed. The resulting output is a weighted sum of the values. The weight assigned to each value is computed based on a compatibility function between the query and its corresponding key. This compatibility dictates relevance. This way, the model can focus on the most relevant parts of the input when producing the output, enhancing its ability to capture relationships and generate accurate results. The paper introduces the scaled dot product attention mechanism, a core component of the transformer architecture. This form of attention computes how much focus should be placed on different parts of the input when processing a sequence, as described in the attention section of the model architecture. The process begins by calculating the dot products between queries and keys. These dot products determine the initial weights, representing the similarity between each key and the query. To stabilize training, especially with high-dimensional data, these dot products are then scaled down. This scaling, detailed in the scaled dot product attention subsection, involves dividing the dot products by the square root of the dimension of the keys. This scaling prevents the dot products from becoming excessively large, which can lead to unstable gradients during training. Finally, a softmax function is applied to these scaled values. The softmax function, mentioned in the scaled dot product attention subsection, normalizes these weights into a probability distribution, ensuring they sum to 1. This probability distribution represents the final attention weights, indicating the relative importance of each value. Multi-head attention enhances the standard attention mechanism by linearly projecting queries, keys, and values multiple times. This approach allows the model to run attention functions in parallel across these different projections. After the parallel computations, the resulting output values are concatenated. This concatenation enables the model to capture different aspects of the relationships within the data. The effectiveness of multi-head attention comes from 3 key aspects. First, linear projections map the inputs to different representation subspaces. Second, parallel attention functions operate independently on each of these subspaces, which allows the model to capture a wider range of relationships. Third, the concatenation process combines the outputs, enabling a more comprehensive feature extraction and a more nuanced understanding of the data. The model architecture section in the paper, specifically the subsection on multi-head attention, provides detailed information on how this mechanism is implemented and why it's beneficial for capturing complex relationships in sequence transduction tasks. This slide will explain how multi-head attention is applied in the transformer model, improving its ability to capture relationships between words and enhancing performance in sequence transduction tasks. As mentioned in the model architecture section, multi-head attention is used in 3 distinct ways. First, encoder-decoder attention lets the decoder focus on relevant parts of the input sequence, ensuring that the decoder gives appropriate weight to the most important words. Second, encoder self-attention enables each word in the input sequence to attend to all other words in the same input sequence. Finally, decoder self-attention allows each word in the output to attend to previous words in the output, maintaining the model's autoregressive property. Let's discuss the position-wise feed-forward networks used in the transformer architecture. Each layer in the encoder and decoder stacks contains a feed-forward network that is applied to each position in the sequence separately and identically. This network consists of 2 linear transformations with a rectified linear unit activation function in between. While the transformations are the same across different positions, they use different parameters that are specific to each layer. The feed-forward network can be viewed as 2 convolutions with a kernel size of 1. The input and output dimensionality of this network is the model dimension, which is set to 512 in the base configuration. The inner layer of the feed-forward network has a higher dimensionality, denoted as DFF, which is set to 2048. This larger inner layer allows the network to learn more complex transformations before projecting back to the model dimension. Now, let's discuss embeddings and the softmax function. Similar to other sequence transduction models, the model uses learned embeddings to convert the input tokens and output tokens into vectors. Following this embedding process, a standard linear transformation and a softmax function are employed to convert the decoder output into predicted next token probabilities. For efficiency and to reduce the number of parameters, the weight matrix is shared between the two embedding layers and the pre-softmax linear transformation. This weight sharing technique helps in improving the model's generalization capability and reduces the risk of overfitting. The transformer architecture leverages positional encoding to incorporate data regarding the order of tokens within a sequence. The paper explains in the positional encoding section. Because the model lacks recurrence and convolution mechanisms, positional encodings are introduced by summing them with the input embeddings at the base of both the encoder and decoder stacks. These encodings share the same dimension as the embeddings, facilitating their summation. Specifically, sine and cosine functions with varying frequencies are employed to generate these positional encodings, and each dimension of the positional encoding maps to a unique sinusoid, which enables the model to easily focus on relative positions between tokens. Now, let's delve into the advantages of self-attention layers over recurrent and convolutional layers, as highlighted in the Why Self-Attention section of the paper. Self-attention mechanisms offer a significant boost in parallelization due to their constant operation count. This is particularly beneficial when the sequence length is less than the representation dimensionality, making self-attention faster than recurrent layers in many practical scenarios. Recurrent layers, on the other hand, require an order and sequential operations, which can limit parallel processing. Furthermore, self-attention connects all positions directly. A single convolutional layer falls short of linking every input and output position, leading to longer paths for capturing long-range dependencies. By connecting all positions directly, self-attention reduces the path length, facilitating the model's ability to learn these dependencies more effectively. Now, let's delve into the training of our models. This process encompasses several key aspects, including data preparation, hardware configuration, optimization techniques, and regularization methods. These components collectively determine how well our models perform and how effectively they generalize to new data. Selecting appropriate settings for each aspect is crucial for achieving effective learning. As described in the training section of the paper, the data we use comes from the workshop on machine translation datasets, specifically encoded using byte pair encoding for efficient processing. For optimization, we employ the Adam optimizer, carefully adjusting the learning rate throughout the training process using a defined schedule. Finally, to prevent overfitting and improve generalization, our regularization strategy incorporates both dropout, which randomly omits nodes during training, and label smoothing, which encourages the model to be more uncertain of each class. Let's discuss the training data used for the models, as described in the training section of the paper. For the English to German translation task, the models were trained on the WMT 2014 English-German dataset, which includes approximately 4.5 million sentence pairs. Byte pair encoding was applied to encode these sentences, utilizing a shared source target vocabulary of around 37,000 tokens. For the English to French translation task, the researchers used a larger dataset, the WMT 2014 English-French dataset, consisting of 36 million sentences. The tokens were split into a 32,000-word piece vocabulary. Sentence pairs were grouped together into batches, considering the approximate sequence length during this process. Key aspects include that the English-German dataset employs byte pair encoding. The English-French dataset has a larger vocabulary, and batching accounts for the approximate sequence length. This slide details the specifics of the training process for the models. All models were trained on a single machine equipped with 8 NVIDIA P100 graphics processing units. The base models, using the hyperparameters described in the paper's methodology section, were trained for 100,000 steps, which is equivalent to approximately 12 hours of training time. The larger models, requiring more extensive training, were trained for 300,000 steps, or about 3.5 days. In summary, the training process involved the use of 8 NVIDIA P100 graphics processing units. Base models were trained for 12 hours, and the larger or big models were trained for 3.5 days. The Adam optimizer was used to optimize the model during training. The learning rate, which determines the step size in each update, was dynamically adjusted throughout the process. Initially, the learning rate was increased linearly during a warm-up phase. This helps stabilize the training in the early stages. Following the warm-up, the learning rate was then decreased proportionally to the inverse square root of the step number. This decay helps the model converge to an optimal solution as training progresses, as described in the optimizer section. To prevent the model from overfitting the training data and to enhance its ability to perform well on unseen data, the training process incorporates several regularization techniques. These methods, which include residual dropout applied to sublayer outputs and embeddings, as well as label smoothing, collectively enhance the model's robustness and performance. Specifically, residual dropout is applied to the output of each sublayer. Dropout is also applied to the sums of the embeddings and positional encodings in both the encoder and decoder stacks, as mentioned in the residual dropout subsection. Additionally, as noted in the label smoothing subsection, label smoothing is employed to prevent the model from becoming overconfident in its predictions and to improve overall accuracy. The transformer model's performance is truly remarkable. As we delve into the results section of the paper, it becomes evident that this architecture achieves state-of-the-art outcomes in machine translation tasks. It notably surpasses previous models in both English to German and English to French translation scenarios, as detailed in the machine translation subsection. Furthermore, within the English constituency parsing subsection, we see that the transformer performs admirably on English constituency parsing, yielding results that are highly competitive with existing models. This ability to perform well in different tasks shows the strong generalization capabilities of the transformer architecture. Therefore, it demonstrates strong generalization capabilities. To summarize, the model establishes new bilingual evaluation understudy scores on translation tasks, achieves competitive parsing accuracy, and exhibits versatility across different natural language processing tasks. Now, let's examine the translation results achieved by the transformer model. In the results section, the paper highlights that the transformer model attains state-of-the-art bilingual evaluation understudy, or BLUE, scores on the 2014 Workshop on Machine Translation, or WMT, English to German and English to French translation tasks. Significantly, the model outperforms previous models and even ensembles. Specifically, the transformer achieves a bilingual evaluation understudy score of 28.4 on the English to German Translation task. Surpassing previous benchmarks. Furthermore, a bilingual evaluation understudy score of 41.8 is attained on the English to French translation task, demonstrating its superior translation capabilities. Importantly, the model accomplishes these state-of-the-art results with less training cost compared to other models. In order to evaluate the importance of the various parts of the transformer model, we performed several model variation experiments. We measured the changes in performance by assessing the English to German translation task. The goal here was to assess the contribution of each part of the model to the overall performance. Specifically, we varied the number of attention heads and their respective dimensions. We also varied the attention key size. And finally, we tested the sinusoidal positional encoding against learned positional embeddings, as we mentioned in the positional encoding section. This slide presents the constituency parsing results, focusing on how the transformer model performs when applied to English constituency parsing. We use the Wall Street Journal section of the Penn Tree Bank to evaluate the model, despite only a small amount of tuning specific to this task. The model demonstrates surprisingly strong performance. Specifically, the transformer model's performance exceeds that of most previously reported models, though it does fall slightly short of the recurrent neural network grammar, as is shown in the results section. Notably, the transformer outperforms the Berkeley parser, even when trained solely on the Wall Street Journal training set, which contains about 40,000 sentences. These results highlight the capability of the transformer to generalize effectively to tasks beyond just machine translation, as described in Model Variations section, indicating its potential applicability to a wide range of natural language processing challenges. Let's look at the key achievements of the transformer model. This model represents a significant advancement as the first sequence transduction model relying entirely on attention mechanisms. It moves away from traditional recurrent layers, utilizing multi-headed self-attention instead. This architectural change leads to faster training times, especially in translation tasks. Notably, the transformer achieves state-of-the-art results in both English to German and English to French translation, surpassing the performance of ensemble models. Looking at the conclusion section, we can see how this model is based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. The transformer also can be trained faster than architectures based on recurrent or convolutional layers and achieves a new state-of-the-art. The paper also outlines several avenues for future exploration. One direction is to extend the transformer model to modalities beyond text, enabling it to process and generate other types of data. Another is to investigate local restricted attention mechanisms to efficiently handle large inputs and outputs. Finally, there is an interest in reducing sequential generation for efficiency. The transformer represents a new and simplified network architecture. Its uniqueness lies in its exclusive use of attention mechanisms, completely avoiding recurrence and convolutions. Our experiments focusing on machine translation tasks demonstrated that it not only achieved superior quality translations, but also offered greater parallelizability and required substantially less time for training compared to traditional recurrent or convolutional networks. This work introduces a new model architecture that relies only on attention mechanisms. This model sets new performance standards in machine translation tasks. Finally, the transformer stands out with its superior parallel processing capabilities and reduced training duration. Attention visualizations offer a window into the model's decision-making process. By examining the attention weights, we can observe how the model focuses on different parts of the input when generating predictions. Visualizing these patterns provides insights into the model's behavior and helps identify potential areas for improvement. Specifically, the attention mechanisms are capable of resolving anaphora, following long-range dependency patterns, and individual attention heads learn to perform diverse tasks. Examples from the attention visualizations section show this behavior by the attention mechanism.